Well, good morning, good afternoon, everyone. Welcome in from across the continent for another exciting broadcast with us here at Exploring by the Seat of Your Pants. We've got some familiar faces in the crowd. We've got some new faces too on YouTube. So welcome in. And if you're joining us for the first time today, we are all about bringing conservation, adventure, and science into classrooms around the world. Now, today's been very exciting. We started off with Dan Vander Kooy talking about the ocean cleanup. We just wrapped up with Dr. Parshadi Patel talking about the life and death of stars. And we get to wrap up with one of my very favorite scientists of all time, longtime friend of the show, Dr. Nathalie Ouellette. So she's been joining us talking about the James Webb Space Telescope, which, as many of you may know, is like the greatest science instrument of all time. It is super, super cool by any standard. I'm not hyping it up too much. It rocks. Now, we talked about it before it even went up into space. It has been up there for a while now, getting some of the best images, giving us a new glimpse at the universe around us. And so today, we are going to get a little bit of an update on the James Webb Space Telescope, what it's all about, how it got up there to begin with, and what it is capturing for us to explore and discover. So without further ado, Dr. thank you so much for joining us again today, and welcome back to the broadcast.
It's always my pleasure.
It is my pleasure having you. Honestly, it's very rare I have someone who is as charismatic as I am, and you just brim with enthusiasm for the universe, and it shines through every single time. So thank you more than you know.
Yeah, I mean, really, it's the fault of the universe. There's so many wonderful things to discover out there. I'm just a conduit for all of those images and those discoveries. And yeah, we're going to go over the James Webb Space Telescope today. Going to do sort of a review of some of the basics, what it is, what it does, why it is so much more amazing than everything we've had before, but also giving you some updates on some of the latest discoveries, including discoveries made by some Canadian astronomers. So very, very exciting. So astronomy. We have been doing astronomy for a really, really long time. And for the most part, we've been using one very single kind of light, visible light, which is the same kind of light that humans can see with their naked eyes. But you might know that there's lots of different kinds of light out there, and they're all encompassed in what we call the electromagnetic spectrum. So here you can see all these different kinds of light. They'll have different names and different what we call wavelengths. So wavelength is sort of like colors, except some of these colors are invisible to the human eye. So here you'll have radio waves, for example, which we tend to associate to sound, and we can hear sounds emitted by those radio waves, but the radio waves themselves are a kind of light. Here we have infrared light, which we associate to heat a lot. We have visible light here, which are the colors of the rainbow that we can see. Ultraviolet light, which you might know you need to protect yourself against using sunscreen. X-rays, which we use in medical imaging. And gamma rays. So gamma rays, the most energetic lights. And if you follow some superhero stuff, that's what created the Hulk. The Hulk is the Hulk because of gamma rays. So lots of these different kinds of lights are invisible for us, but the universe is shining in these kinds of light. So we need special tools in order for us to look at these different kinds of light. And one of these tools is the James Webb Space Telescope. And it is looking at infrared light, which I mentioned is something that we cannot see with our human eye, but lots of different things in the universe shines brightly in the infrared light. And we'll go over some of those things. So the James Webb Space Telescope is a wonderful telescope, gigantic, about the size of a 3-story house. It's the largest space telescope we've ever sent up into space. And it is a huge collaboration. Over 10,000 people worked on this together. So it's a project led by NASA in the United States, but there's also contributors from the European Space Agency. And those two teams together, they formed the Hubble Space Telescope, which is sort of like the father or the grandfather of the James Webb Space Telescope. It still works, but it's getting older now. And so we've been sort of planning for the James Webb Space Telescope for a while to sort of succeed to his legacy. But for the Webb telescope, very exciting for us in Canada, the Canadian Space Agency is also part of this team. And this is the largest space mission ever. So the fact that Canada is part of the space astronomy mission is super, super exciting. So I'm the outreach scientist for the Webb Telescope in Canada. I've been on the team since 2018. Very, very exciting. When I first joined, it was supposed to launch just a few months after I joined the team, but there were a few delays, and partially because it's such a complicated machine, we needed to really test it really well. So I've had the pleasure of working with astronomers and scientists from all over the world working on this mission and sort of acting like a bridge between the science teams and the general public and kids and classrooms to make sure that you can all discover what the telescope is doing. So I got to visit the telescope in 2019 while it was being tested in a lab in California. I got to see how big it is. It looks kind of small next to me, but because it's far back in that room, so you can actually see a human right there wearing what we call a bunny suit so that they can stay clean and make sure the telescope doesn't get dirty. And you can see how much smaller that human is compared to this giant telescope. So I love this picture of me, but the picture that I like to show my commitment to this mission is this picture instead. So right before the launch of the telescope in 2021, I made a Halloween costume, which is a 2 scale model of the telescope, and I wore it when I gave out candy. So I love to do stuff like this when I'm doing outreach. I want to show that space and astronomy and science is fun, and science can be serious, but can it also be like fun and funny, and you don't have to take yourself too seriously when you're doing it. So I hope that everybody can imagine themselves as a scientist. So this is a project that's been in the works for a long time, for decades essentially. And finally, in 2021, December 25th in the morning of Christmas, the telescope was launched aboard a rocket called Ariane 5. And it is one of the largest rockets that we have now. And we needed a big rocket because it's such a big telescope. But even though the rocket was so big, we couldn't fit the telescope inside of it unless we folded it onto itself like a piece of origami. So this, you can see that the telescope is all folded up on itself. It's been launched into space. And then over the course of 14 days, it needed to unfold. So this was a very, very complicated process. 300 different mechanisms needed to deploy and activate in order for the telescope to completely unfold over time. And lots of people ask me, that sounds like really, really risky. Can you just park the telescope next to the Earth, unfold the whole thing, and then if something gets stuck, you can maybe send astronauts to go fix it? Well, the issue is this telescope needs to go very far from the Earth, 1.5 million kilometers or 1 million miles away from the Earth for it to work properly and look at the infrared light. And it needed that sort of push from the rocket in order to get there with the amount of fuel that it had. And so if we put on the brakes and we parked it next to the Earth, we would lose all that energy. So while all this is going on, you can actually see at the bottom of the image that the telescope is moving through space. It passes by the moon. Its final destination is 4 times farther away than the moon, and it's deploying all these different components. Now, you saw its solar shield, its big metallic piece here that unfolded. That's about the size of a tennis court, and it protects the telescope from the very intense heat and radiation of the sun. And then you have the mirror, the golden mirror, very iconic, which needs to be unfolded as well. It's 6.5 meters wide, and it's made up of 18 little segments that are in the shape of a hexagon, and they're all coated in gold because gold reflects infrared light really well. So everything went really, really well. We were really happy. We were very scared when this was happening because this is all happening long distance from us. After 14 days, it unfolded. An extra 14 days, it arrived to its final destination, 1.5 million kilometers from the Earth. So in Canada, we contributed a double instrument to the mission. So there's lots of different instruments you could put on a telescope. The mirror is what collects the light, but then the light gets redirected in the back of the telescope. And there you have cameras, you have specialized tools called spectrographs, and they can do all kinds of cool science with that light that you're collecting from faraway objects in the universe. So, this is Canada's contribution here. It's this big golden box at the center. And we gave the mission a 2-for-1 deal. It is a double instrument, and the top instrument here is what we call the fine guidance sensor. It's just a camera, basically, that allows the telescope to lock on to a target. So the telescope is moving around in space, but it wants to take nice, clear pictures. And in order to do that, it needs this guiding camera to do that. So even though it's not a scientific instrument that does science, it is critical to the mission. And so we provided that. And underneath, we have what we call the NIRIS, for Near Infrared Imager and Slitless Spectrograph, or NIRIS. And that is the science instrument that Canada provided. So that can take pictures, it can take specialized data called spectra, and that allows us to understand the nature of distant objects like exoplanets and galaxies. So all of this was created over several years by hundreds of scientists and engineers in Canada, led by the Canadian Space Agency, but with people at the University of Montreal, at the National Research Council in Victoria, and Honeywell, which is a private company. So it's a big collaboration that made this possible. So that's sort of like all the technical stuff about Webb. But of course, Webb wants to understand the universe. It wants to understand how different objects like stars and black holes and galaxies and planets work. It wants to observe these things. And so, what is Webb observing now that it's been operating for almost 2 years? So, one thing I love about the Webb telescope is that it's super useful for basically the entire astronomical community in the world. So, you know how some doctors they specialize in heart, or they specialize in the brain, or they specialize in the eyes, but you also have some doctors that are what we call general practitioners or family doctors, and they sort of have to be able to do a little bit of everything. That's sort of what the Webb telescope is. It is a general practitioner of telescopes. It can do a little bit of everything in astronomy. And so we can sort of break it up into 4 big categories. The first is alien worlds, a very popular one. Now, alien worlds just mean worlds other than our own planet Earth. So it can be things in our solar system, but it can also be planets that are beyond our solar system, something that we call exoplanets. They're planets that orbit stars other than our own sun. We can also understand the life of stars. So, my friend Prashadi, just before, sort of talked about the life and death of stars, and the James Webb Space Telescope is a really good tool to understand that life cycle, partially because it's a very dusty process, and infrared light is a super good tool to study those dusty areas during the life and death of stars. Similarly, we want to study how galaxies form and evolve over time, and they can form and evolve over billions of years. And they often form and evolve in groups. So they'll interact together, sort of like what I like to think of as a herd of animals. They'll interact, they can collide, they can merge and fuse together, and they can affect each other's evolution. And one of the main reasons why we built this telescope is we want to look as far back into the history of the universe as possible. Because you may know this, telescopes not only allow us to see far back in distance, but also far back in time. They can act like time machines because it takes a long time for the light of these distant objects to travel those long distances to us. What we observe is very old light. So if we say something is 10 billion light years away, we're not actually seeing it as it is now. We're seeing it as it was 10 billion years ago. So we want to look almost to the very start of the universe, close to the Big Bang, using the James Webb Space Telescope. So we're going to look at some of the discoveries that the telescope has done, some of the beautiful images it's collected. And starting close by in our solar system, this is a wonderful image of Jupiter that allows us to see lots of different things. So maybe some of you got to see a few weeks ago the aurora here on Earth. So these beautiful light shows in the sky that are caused by solar wind particles that interact with the Earth's atmosphere and magnetic field. And Jupiter, just like a lot of other planets, also have aurora. So you can actually see the aurora on Jupiter right here on the North Pole and right here in the South Pole. You can also see some of Jupiter's rings because Saturn is not the only gas giant planet with rings. Jupiter has very thin rings as well. You can see this big spot. Usually, when we take color images, this looks red. This is a big hurricane on the surface of Jupiter. And you can see lots of little moons around Jupiter all around here. So, lots of beautiful detail. One thing I love to mention about this picture is beyond just the picture itself, it's who made the picture. So it wasn't actually NASA scientists who created this image. The telescope took the data, but then scientists usually have to treat the data and do special things with the data to create these beautiful images. And the person who did that is a student who's a citizen scientist. Her name is Judy Schmidt. She's a student not in astronomy, in something else. She lives in California. She's just a lover of space and a lover of astronomy. And she taught herself how to use data from space telescopes like Hubble before and now with James Webb to make her own images. And she created this image and NASA loved it so much it decided to include it in its normal roster of images for the Webb telescope. So even you, if you're like really excited and you don't want to wait until university and to have a PhD to do astronomy, you can teach yourself how to make these images using data that's publicly available from these space telescopes. Now, moving a little bit farther away, still in the solar system, we have Neptune and Uranus, which are the smaller of the gas giants. We also call them the ice giant planets. And I really love these images because these are two planets that have been pretty neglected by space exploration in our solar system. They've never had a dedicated probe mission before. So that means that the people studying these planets have not had very good data for decades. Basically, since the Voyager probe flew by them, they didn't even stop by these planets. They just sort of flew by and took some pictures on their way out of the solar system. So now we can see beautiful detail on these ice giant planets. We can see the rings around both Uranus and Neptune here. We can see lots of moons around Neptune, including the most important moon, Triton. And you can see lots of details in the atmospheres of these planets too. You can see bands of clouds. You can see sort of like this polar ice cap on Uranus there. So these are the best images we have of Uranus and Neptune in over 30 years, thanks to this telescope. Now, if you want to go farther away from our solar system, we can observe alien worlds. So I mentioned these exoplanets. These exoplanets are beyond our solar system. They orbit stars other than our sun, but it's very hard to spot them because they are very small and they're orbiting bright stars. So when you see pictures like this, they are always what we call artistic representations or illustrations. They're drawings, but they're not just wild guesses. We have a lot of information about these planets, like how big they are, what color they might be, what kind of gases they would have in their atmospheres. And we work with artists to try to make realistic representations of these planets. But then, how can we study them if we can't really see them? So we have to be clever. We have to use what we call an indirect method. So we're not looking at the planet itself, we're looking at the effect of the planet on its star. So we have specialized telescopes other than James Webb. Their whole point of living mission is to simply stare at lots and lots of stars, and eventually they'll notice that some of the stars, the brightness will go down a little bit. And that is an indication that something passed in front of the star and blocked some of that light. And if it blocks more light, it means the object that blocked the light is bigger. So that is a clue that there's a planet that passed in front of that star, that's orbiting that star, and we can get information about how big that planet is. So this is something that we call a transit. It's sort of like an eclipse, but it's a faraway planet passing in front of a star. And the telescope, the James Webb Space Telescope, can study these stars and these planets during these transits and find out more information about the planet. So it did that for this planet here called WASP 39b. It's a big, puffy planet like Jupiter, but very, very close to its star. It only takes 4 days for it to orbit around its star. It's very, very hot. And so this is 700 light years away, and it was one of the first targets that the Webb telescope studied using this method. And it was a team of over 100 scientists that studied this, including many of my colleagues at the University of Montreal. So these are all astronomers that I work with at the University of Montreal. They studied this planet here as it passed in front of its star, and they took what we call a spectrum. Now, a spectrum, when we look at this as scientists, it looks like a bunch of wiggly lines, essentially. But these wiggly lines sort of act like a fingerprint or a barcode, and that wiggles and those wiggles and that barcode tells us exactly what's in the atmosphere of that planet. So many different instruments on the telescope took a spectrum of that planet, including the Canadian instrument nearest that I mentioned. And using this information, we were able to determine in the atmosphere of this planet, there was carbon dioxide, there was water vapor, that there was potassium. The same potassium you have in your bananas is in the atmosphere of this planet. And we were able to do that from 700 light years away. Very, very exciting. But you might say to yourself, okay, this is a big, hot, Jupiter like planet. Not really the best place to look for alien life. Now, we can use the same technique on planets that are more like Earth. Now, this is K2-18b. It's a possible ocean world, so it might be covered by a thick layer of liquid water. And we did the same thing here. We took a spectrum of this planet. And again, we found the fingerprint of the atmosphere of this planet. We were able to find methane, carbon dioxide, but there's one molecule, especially called dimethyl sulfide or DMS, that is very intriguing because here on Earth, the only way you can make DMS is through life, through biological activity. So this is what we call a biosignature. And this is what we look for when we're looking for alien life out in space. We're looking for these molecules that need life to exist. So this is a tentative signal. We need to confirm it. It's possible that there are other ways to make DMS on other planets that don't require life, but it is a very hopeful first sign that maybe we are on the brink of discovering alien life for the first time. If we go to stars here, where are stars born? They're born in these really dusty areas called nebulae or star forming regions. And this is what we call the pillars of creation. So, this is an image in the infrared taken by the Webb telescope. And you can see nestled in all of these gas pillars, these stars that are being formed. And you can actually see in the tips of the finger right there and right here, those red cracks that almost look like lava or magma. Those are newborn stars in the first few million years of their life, nestled in these sort of gas caverns. And so we're able to study the birth of stars using Webb. And I mentioned that infrared is really important here. So this is the same part of the universe, the pillars of creation, as seen in visible light by the Hubble telescope and in infrared light by Webb. And you can see a huge difference between the two images. And that is because infrared can pierce through the dusty areas in the star forming regions. So it's almost like having X-ray vision, but it's infrared vision, and you can see the birth of stars hidden behind all of this gas and dust. Now, you might know another nebula called the Orion Nebula. It's beautiful. You can actually see it in our sky around in the winter time. And this is a nebula where not only can we see the birth of stars like this one here and this one here, we can see how these really, really big stars being born is injecting a bunch of energy in its surrounding area. And there's one scientist at Western University. Her name is Alice Peters. She's leading this team trying to understand how the birth of these stars is affecting their environment. And it's sort of like a feedback loop. They're not isolated things, they're all working together to try to make these stars be born over time. But eventually, a star will die, and depending on the type of star, it will have a different kind of death. So, most stars will turn into what we call a planetary nebula. They'll look like the ring nebulas that you have on either side of this image here. You'll have the star that'll puff up, blow out its exterior, and all that's left over is a zombie star called a white dwarf. Or you can have a very, very massive star, much bigger than the sun, that explodes in a supernova explosion and sprays out all its guts essentially. And you have what we call a supernova remnant, like Cassiopeia A here. And all the dust that you can see here in these web images will end up re injected in the environment around them and be recycled into new stars. So, this will lead to the creation of brand new stars later down the road. We can also study the formation of stars in entire galaxies. Now, this is a huge project called FANGS, and it's led by lots of people around the world, including these three scientists that are at the University of Alberta. And they took these 19 images of these galaxies that are close by, and they almost look like coral or seashells, or even like maybe a human eye. And here, all the bright filaments you can see, those are knots of stars as they're being formed. But as stars are forming, they're blowing out lots of wind, and they're creating these bubbles of emptiness around them. So these people are able to study how the forming of these stars is affecting the very structure of the galaxy that they find themselves in. If you like galaxies, though, this is really the image for you. This is the Webb Deep Field of Galaxies. In this image alone, there are 7,000 galaxies, and it's in a tiny part of the sky. So many galaxies, so many colors, and we've been able to study lots of these individual galaxies. And one galaxy in particular, nicknamed the Sparkler Galaxy, was studied by Canadian scientists at the University of Toronto. And they were able to find these little sparkles around it, these dots. And they wanted to understand what those dots are. Now you can only see the dots in the Webb image. In the Hubble image, it's too blurry. And they discovered that these little dots were actually what we call globular clusters. They're these treasure troves of millions of stars that were all born together. And these are some of the oldest globular clusters we've ever been able to observe in the universe around the Sparkler Galaxy. For a long time, we've been trying to study these very, very early galaxies, and they've been only little dots because our telescopes have not been very good. But now, with the Webb telescope, we've been able to basically discover this whole new category of different galaxies. And we've sort of nicknamed them fun things like surfboards and pool noodles and frisbees and volleyballs, depending on how long and thin they are or how big and round they are. Before, when we were studying these faraway galaxies, they just looked like dots. Now we can actually see detail, spiral arms, these little knots with lots of stars forming in there. So it's a really wonderful time to do astronomy. So if you're interested, there's lots more results that you can find online at www.webtelescope.org. This is just the tip of the iceberg. We've been operating for about 2 years, but we're hoping to go for maybe even 20 more years. So stay tuned for even more fantastic results later on.
Oh, Nathalie, as always, such a thrill having you on. And we got more questions already in the chat that we could possibly take in one broadcast. So that is a really good problem to have. I'm going to make sure our registered classes have that link. Web.nasa.gov has a lot of great stuff too. So there's lots of ways to keep learning going. Honestly, when I was a kid, I would have died to have the opportunity to following along with active space missions like you guys have today. So it's a really lucky time to be interested in astronomy. And that was an amazing primer into some of this cool science. Now, we're going to dive in with questions. We've got a couple live classes with us. So George Webster, I know you guys came in a little late. If you have questions, let me know in the chat. Farmington, Miss Dillon's class, I will come to you guys in a second. We'll take some from our YouTube group first. Miss Jacques' class wants to know, so many questions, geez. Oh, let's take this one. How many exoplanets has the telescope identified? Hmm.
So that's a good question. So the James Webb Space Telescope isn't really an exoplanet finding machine. It really is more used to do what we call follow-up observations. So there are other telescopes like the Kepler telescope or the TESS satellite, and they're the ones that stare at thousands and hundreds of thousands of stars at once to discover a new exoplanet. And those have been able to detect thousands of exoplanets. We know of about 6,000 exoplanets now. But they can't really give you a lot of detail about the nature of those planets. So once they detect and discover a planet, they give the information to the scientists, and then scientists can do the follow up observation with the Webb telescope to discover things like what are the molecules and the atoms in its atmosphere and what temperature it has.
Yeah, very cool. We've got a bunch of questions about that too, so I'm sure we'll get to them over the next 10 minutes together. George Webster Elementary, if you guys want to come on in, your mic is unmuted. You are good to go for a question. Hey, guys.
Oh, I have a question. What was the most groundbreaking discovery you made?
Ooh, no pressure, Natalie.
Ooh, that is really tough, and I think it depends a lot on what you're interested in. So, like I said, because the telescope can do so many cool things, it has a little bit of everything for everyone. But I'd say the thing that I find the most fascinating and has caused sort of like a lot of trouble for astronomers is those really early galaxies that we have been observing. They look a lot more mature and a lot bigger than we were anticipating based on what we know about the early universe. It's sort of like we snuck into the hospital and we looked at a nursery expecting to see all these baby galaxies, but instead we saw all these teenagers there and we're like, how did they get so big and so old so quickly? So that's a big mystery that we have now. And so we were hoping the Webb telescope would help, but it's actually given us more questions, but we need to take more observations to answer those questions.
Oh, thank you for that analogy. That absolutely makes my day. That's marvelous. We've had a question online, and I find this one interesting. Is there a wavelength smaller than gamma rays? You're talking about the electromagnetic spectrum to begin. What's the deal? Is gamma the top?
Yeah, so basically, you can go to smaller and smaller and smaller wavelengths or larger and larger and larger wavelengths. But at some point, anything that's smaller than a specific wavelength is all gamma rays, and everything that's larger than a specific wavelength is all radio waves. So there's nothing smaller than gamma rays.
Okay, good to know. Farmington, Miss Dillon's class. I think your tech should work. I'll bring you in, and if not, you have a bazillion questions on YouTube for us. But welcome in. You opened up a second device. When you do that, it causes the reverb. So play around with that. You can always mute the mic and speaker on one. There we go. We should be good. Hey.
Yeah, sorry.
You're good. Come on up.
Come on, we're gonna come up here.
Come on over. Yeah. Come see us. All close.
Sorry. You got me right as we were switching.
Yeah.
I was there gold and now see because it's gold.
So why is the mirror gold? And what was the second question? How do we make it gold? All right. So yeah, the mirror is this beautiful golden color because there really is a very very fine layer of gold on it. And that's because gold is the best material to reflect infrared light. So when you have a big mirror on a telescope, you want to reflect it. It's not a flat mirror. It's sort of gently curved to redirect all the light into what we call a secondary mirror, and that funnels all the light into the scientific instrument. And you want to be able to reflect almost 100% of the light you're capturing in order to not lose any of that light. And so if you're looking at visible light, something like aluminum, a silver color, will be really good. But for infrared light, gold is really the material of choice. So that's why we covered the mirror in gold. But it looks very impressive. But if you took all that gold on the mirror and you rolled it up into a ball, it would be about the size of a golf ball. So it's a very, very thin layer that they put all over the mirror for that.
I honestly, you do have a gift for analogy. It's fantastic. I've heard this about gold, though. And so for our students, like gold looks like, this sounds silly, but when gold is like one atom thick or something crazy like that, it looks like gold. So you can have an insanely thin sheet of gold. Gold plating is like this, where you go, oh, wow, it's all gold. And it's not a thick thing of gold. It's very, very tiny. Golf ball, eh? Wow.
Yeah, it's like 6 atoms thick.
Yeah, they're really, in the scheme of the world, there hasn't been that much gold actually found. I forget what the analogy is, but like all of it could fit in like a school quite easily. So it's a very valuable material for a reason. Great question, guys. All right, Ms. Jacques wants to know, does it help us identify the composition of planets?
So that's a really great question. And so when we were talking about exoplanets, and I was talking about there's carbon dioxide there, there's potassium. I'm talking about the atmosphere of the planets. So that's all the air that's around the planets. And that's a lot easier for us to determine because the light of the star in the background is actually passing through the atmosphere and giving us that information. But think of Venus, for example. If you've ever seen a picture of Venus, a real picture of Venus, it looks like this big ball of gas, and that's because it has a thick atmosphere, but there's a solid ground under there, but you can't see it because it's blocked out by all those clouds. So it's actually quite hard to tell what the actual rocky part of a planet is made of. So we have to be clever again, and we have to do things like, if we know the size of the planet and we know the mass or the weight of the planet, that tells you the density of the planet. And we know, for example, rock is denser than water, which is denser than air. So by knowing the density, we can try to figure out what kind of materials the planet could be made of to match the density that we did find. But it can be like different proportions of rock versus water versus air. So it's very hard to determine the composition of the rock part of the planet, actually.
That's a very cool answer. I like that very much. And I like the next question too, because it's one we've never gotten before on this, and it's a very important one. What did James Webb do to get the telescope named after him?
Yeah, that's a great question. And actually, in the question, it says, what did the scientist James Webb do? And he wasn't actually a scientist or an astronomer, and that's quite rare. Usually, telescopes are named after astronomers or scientists. James Webb was actually the administrator, sort of like the man in charge at NASA in the 60s during the Apollo missions. So the Apollo missions is when NASA really wanted to get to the moon. And it's sort of like where we're picking up now with the Artemis missions. And so he did a lot of work to try to make NASA get to the moon first before the Soviets. He was an administrator. And so he didn't do science, he helped the scientists do their jobs. It's always tricky naming things after people because people are human, humans make mistakes, humans can be good and bad and lots of things. The way that I like to see it, though, is often scientists get a lot of the credit for these big telescopes and scientific missions, but all kinds of people are needed to make them work, including people like engineers, administrators, project managers, secretaries. Everybody that works on the team is important. And so the fact that it was named after an administrator, I like to think of it as it's a nod to all the non-scientists who make these wonderful projects work.
That's a beautiful way of thinking about it. This is the thing that we keep coming back to all day long. We were talking with the ocean cleanup earlier today, and they mentioned that there's a bazillion roles. Like, you don't need to be an engineer or an astrophysicist or astronomer to be involved in these great projects. If you want to clean or do business or do law or be a cook, I mean, there's a bazillion things that you can do to get involved in really making a positive difference to these grand, exciting scientific projects. I think that's a really
Absolutely.
important. So thank you for segueing the question there. Nathalie, before we wrap up, because time flies and you're having fun, I'm just going to take one more question from online, and then we'll sort of get a final message and bring in our classes to say thank you and farewell. So our question is, in addition to gold, what is the other material of the mirror of the telescope? Like, what else do we build it of?
Yeah, that's a great question. So, when we're building telescopes here on Earth that are looking at visible light, the sort of silvery part, that'll be aluminum. That's what reflects it. But we'll have a sheet of glass over top to protect that delicate aluminum. But glass is quite brittle and quite heavy. And so, we wanted to send this telescope up into space, we needed something that was lighter, more robust, more solid, that could withstand the dangers of space, and also could withstand the extreme temperatures in space. And so we chose a material called beryllium, which has a lot of the similar properties of glass, but is more expensive because it is more solid and lighter. So the majority of the mirror is actually made up of beryllium. There's just a fine coating of gold on the beryllium.
Interesting. I didn't know. This is honestly, like, I've done probably 10, 15 programs with you, and I've learned the most this time. This has been some really great questioning from our classes. So a big thank you to Missouri, Ontario, Maryland, BC, all our groups from around North America for joining us today. Nathalie, before we wrap up, is there any final message you want to leave us with about the James Webb Space Telescope or astronomical discovery in general?
So we're just wrapping up its second year. It's really exciting. There's probably going to be like a cool second year anniversary image that's going to be released in July, and we're going to be starting the third year of operations. And the new programs were just announced a few months ago, and this is the most that Canada's ever had in terms of time during a year of operations. So you should expect lots of really cool results in the next year, including from Canadian astronomers. So that'll be really cool.
Woohoo! Can't hardly wait. I'll be watching the news feeds closely the entire time. Nathalie, as you know, we bring in all the classes to say thank you and farewell at the end. So Miss Dillon's class, Farmington, if you're still around. George Webster Elementary, thank you both so much. YouTubers, thank you so much. Have a wonderful day, guys, and bye for now, everyone. We'll see y'all soon.